Hello guys, welcome back to my channel. And in this video, just like my previous video, we are going to evaluate another infinite series. And this is going to be with a different technique than most of my conventional videos in the infinite series playlist. So let's get started. Okay, so as I said, we have an infinite series. Let's call it S, which is defined as basically the sum from n equals 1 to infinity of minus 1 to the nth power times the sine of n divided by n cubed. And you can try all sorts of things that you want, but this series we are going to evaluate using one of the most powerful techniques. Actually, arguably, if you really want to debate, then it's the powerful technique of calculating such infinite series. That's basically using Fourier series, or you can say Fourier analysis. So I'll like to give you a brief recap. We did use this in I think one of my videos. I don't remember which, but there was a mention of this in one of my videos. And the basic idea is, if you have a function, say f of x, on some periodic interval, say minus pi to pi, this is the most common interval that we work with, then that function f of x can be represented as some constant a naught over 2 plus the sum from n equals 1 to infinity of a sub n times cosine of um, a sub n times the cosine of nx added with bn times sine of nx. So a sub n and b sub n are basically coefficients that change with n, coefficients that vary with n. So coefficients that change with n. And that because of orthogonality, there is a nice way of finding a sub n and b sub n and even a naught. So in the case that our interval is from minus pi to pi, we have basically a naught is equal to 1 over 2 pi, this is specifically for this interval, 1 over 2 pi times integral from negative pi to pi, again specific to this interval, of just f of x dx, whatever function we chose. And similarly, a sub n has the formula 1 over pi times integral from negative pi to positive pi of f of x times cosine of nx dx. And if you can see the pattern, bn will be 1 over pi times integral from minus pi to pi of f of x times sine of nx dx. But here's a challenge. Here's the real challenge. Well, the challenge is, we have the entire theory of Fourier series and Fourier analysis, but we don't know what function f of x to choose actually. Well, now that requires practice and some really good intuition. So my intuition tells me that if you have a series with say sum from n equals 1 to say infinity of some weird function in the numerator divided by n cubed, then we should consider something of the nature f of x equal x cubed. So 1 over n cubed. So if you have a n cubed in the denominator in the original series, then you take the function x cubed. So similarly, if you had something like series from sum from n equals 1 to infinity of some numerator divided by say n to the pth power, then our f of x, most logical thing to take would be x to the p. This observation comes with a lot of practice. So if you just play around with taking arbitrary f of x's and just try to figure out their Fourier coefficients and try to construct the entire Fourier series, you'll probably see some you probably come across some clever observations like these. So as I said, f of x is going to be x cubed because we have n cubed in the denominator of this original series. So having defined f of x equal to x cubed, we need to find all of these values of a naught, a sub n and b sub n. So we are going to have to do three separate integrals, 1, 2 and 3. So let's first look at 1 on a fresh page. See you there. So as I said before, a naught is just going to be 1 over 2 pi times integral from minus pi to pi of f of x dx, but f of x, as I just said, is x cubed. So this becomes 1 over 2 pi times integral from negative pi to pi of x cubed dx. Integrating this is really easy. You divide by the new power, which is going to be 4. So 1 over 4 times 2 pi is 8 pi in the denominator, and x to the 4th evaluated from pi to negative pi. This will be 1 over 8 pi times pi to the 4th minus negative pi, but the whole thing to the 4th. So the negative 1 to the 4th power is just going to be 1. So you basically get rid of this. So pi to the 4th minus pi to the 4th is going to be 0. So a naught simply evaluates to 0. Fine, this is trivial, right? Where's the interesting part? Well, let's look at the cosine part now. So again, using the formula a sub n, which is the coefficient of the cosine term in the Fourier series, can be calculated as 1 over pi times integral from minus pi to pi of f of x, but it's not alone, times cosine of nx dx. So and we know f of x is nothing but x cubed, so this becomes 1 over pi times integral from minus pi to pi of x cubed times cosine of nx dx. And there is actually no need to calculate this integral, because if once we show that this function entirely is going to be odd, then calculating an integral over a symmetric region of an odd function will give us 0. We know that. I mean, people who have really good observation skills and practice in definite integrals will notice that. But I wanted to give you guys some practice in terms of how to approach such integrals, and one nice way of approaching them is using integration by parts. So you have to differentiate this boy here while you integrate this boy here. So we just integrate cosine of nx, we end up with n outside, right, because of the chain rule. X cubed times sine of nx evaluated from negative pi to positive pi minus 3 times, we're differentiating this, integral from minus pi to pi of x squared times the sine of nx dx. And let's just plug in everything in this term and see what happens. So we have pi cubed times sine of n pi minus pi, the whole thing cubed, sine of negative n pi, but if you guys know extensive trigonometry or just even basics would do, notice that sine of any integer n, and n is always going to be an integer, right? Because in our Fourier series we had sum from n equals 1 to infinity, so n is always going to be an integer, and the sine of an integral multiple of pi of the integer multiple of pi, sine of that is always going to be 0. You can probably draw your angle map that we draw usually, something like this. We have 0 pi, this is just 1 pi, then this is 2 pi, 0 pi is also 2 pi. So all integral multiple, sine is 0 here, sine is 0 here. So anywhere you go, any integer times pi, sine of that is always going to be 0. So all of this term basically goes to 0. So all we are left with is this negative 3 over n pi times integral from minus pi to pi of x squared times sine of nx dx. And now we can take the minus in to compensate for the antiderivative of this sign, which is going to be negative cosine. So 3 over n squared, because of, again the chain rule reversed, n squared pi, negative compensated, we have x squared, and cosine now of nx evaluated now from minus pi to pi, minus 2 times, differentiating, minus pi to pi x times cosine of nx dx. And let's just briefly evaluate this term. So we have pi squared and cosine of n pi minus negative pi, the whole thing squared is again pi squared, and cosine of minus n pi. Well, cosine of say minus theta is just cosine theta, so this expression and this expression is same, and this expression and this is same. So an expression subtracted from itself is going to result in 0. So this thing again goes to 0. So we just have now minus 6 over n squared pi times integral from minus pi to pi of x times cosine of nx dx. And we can just simply calculate this now. This is going to be negative 6 over, well, n cubed, the antiderivative, times pi, and the x times sine now of nx, we're integrating the cosine, minus pi to pi, minus, well, the derivative of x is just 1, so integral from minus pi to pi of sine of nx dx. And again, you have sine of n pi if you plug everything. So like this case above, even this thing is just going to be 0. So all we're left with is 6 over n cubed pi times integral from minus pi to pi of sine of nx dx, which can be written down as, again, you have to, if you want to compensate for the antiderivative of the sine, you need to take a negative 6 over n to the 4th times pi for the antiderivative, and then this is n. Well, cosine of nx evaluated from minus pi to pi, again cosine of n pi minus cosine of negative n pi, and cosine is an even function, so by this property again this is going to go to 0. So well, look at that, again trivial, right? All this work of integration by parts for nothing. This is trivial. Let's pray almost that the sine component of this Fourier series is not 0, otherwise you'll have f of x equals 0, because all of the other terms will be 0 if the sine is also 0, and x cube can't be 0 for all values of x. So we are almost certain that b sub n, or the sine coefficient, cannot be equal to 0, otherwise we've broken math and that never happens. See you on a fresh page. So again, we have sine component b sub n is equal to 1 over pi times integral from minus pi to pi of f of x times the sine of nx dx. And again, we know that f of x we define to be x cubed. Plugging that in, we have 1 over pi times integral from minus pi to pi of x cubed times sine of x dx. And this we have to evaluate like we evaluated its cousin, the cosine, by integration by parts. So, well, we take a negative out to compensate for the antiderivative of this sine of nx and then divide by n, again for the antiderivative part, minus 1 over n pi. We have x cubed, antiderivative of sine nx is cosine, compensated everything else, nx, evaluated from minus pi to pi, and minus 3 times integral from minus pi to pi of x squared, we differentiated that, cosine of nx dx. And now let's just look at this thing. So we have pi cubed times cosine of n pi minus pi cube, right? It was minus pi whole thing cubed is minus pi cube. Minus of minus, that is plus pi cubed, and then again cosine of is even, so cosine of negative n pi is cosine of n pi. So this expression is repeating. So we have 2 pi cubed times cosine of n pi. But an interesting fact to note that we can actually write a shorthand form for the cosine of n pi. That's because notice how the cosine behaves. So if you have, say, an even multiple of pi, so 0 pi, 2 pi, this is also 4 pi, all this point, this angle is can be written as 0 pi, 2 pi, 4 pi, so all even multiples of pi. And at this point, cosine of all these values is 1, right? Cosine of 0 is 1, cosine of 2 pi is 1, and this angle is 180 degrees almost, which is the most smallest value of this angle can have, say pi, 3 pi, 5 pi, or odd multiples of pi. These are odd multiples of pi, these are even multiples of pi. The cosine will have minus 1. So we can write the cosine is minus 1 to the n, where n depends on what multiple of pi you have. So, and that's appropriately the case here, because n is again going to be an integer, so n will determine what multiple of pi we have. So if n is even, then we have an even multiple of pi. So if n is odd, we have an odd multiple of pi. So cosine of n pi can best be represented in shorthand form as minus 1 to the n, because if it's an even multiple, we have minus 1 to an even power, which is 1, like we have here. And if it's like an odd multiple, minus 1 to an odd power is negative 1, like we have here. So all of these properties are satisfied. So indeed we can express our cosine of n pi in this way. Okay, so this expression that we had is basically 2 pi cubed, so 1 over minus 1 over n pi as it is. This is 2 pi cubed times cosine of n pi, which we can write as minus 1 to the n. And we still have the other part as it is, right? So minus and minus will make a plus 3 over n pi times the integral from minus pi to pi of x squared times cosine of nx dx. Okay, fair enough. Now we have a, well, this is just as it is. We can probably cancel out a pi over here. So we have a 2 pi squared, and we can take this negative with this negative to have minus 1 to the n plus 1 power divided by this n. And now integration by parts again. So 3 over n squared to compensate for the antiderivative pi, and we have x squared times sine now of nx evaluated from minus pi to pi, and minus integral from minus pi to pi of now 2 times x times sine of nx dx. I hope by this time you're pretty fluent with the idea of integration by parts, so I'm not explaining every step. So notice that because of this sine of n pi, it doesn't matter what this x squared value will take on this interval, but all of this will go to 0 because of this sign. So finally we have minus 1 to the n plus 1 times 2 pi squared over n, and we have a negative 6 over n squared pi times integral from minus pi to pi of x times sine of nx dx. Now one final time integration by parts. So minus 1 to the n plus 1 2 pi squared over n. Again compensate the negative 6 over n cubed pi times, well, x times cosine now of nx, evaluated from minus pi to pi minus integral from minus pi to pi of, well, derivative of x is 1, so just cosine of nx dx. And finally we are all left with, well, let's just evaluate this expression quickly. So evaluating this expression, we have pi times cosine of n pi minus of minus pi is plus pi, and cosine of minus n pi is cosine of n pi. So this is 2 pi times cosine of n pi appropriately. So we have minus 1 to the n plus 1 times 2 pi squared over n. This is going to be 12, because of this 2 over here, pi times cosine of n pi is minus 1 to the n, right? Divided by n cubed pi minus 6 over n cubed pi, and we can calculate this integral easily. We have an n to the 4th and a sine of nx evaluated from minus pi to pi. And again, sine of n pi and minus n pi are both 0, so this entire term will go to 0. So all we are left with finally, you can cancel the pi's, minus 1 to the n plus 1 times 2 pi squared over n plus minus 1 to the n times 12 over n cubed. That's basically your b sub n, or the coefficient of the sine in the Fourier series. Okay, so we're back to this page, and we know we calculated everything. A naught is 0, a sub n, or the cosine part, is completely 0, and we calculated b sub n, right? So basically f of x can be expressed as the sum from n equals 1 to infinity. And what was b sub n? Well, 2 pi squared, and with minus 1 to the n plus 1 here, divided by n plus minus 1 to the n times 12 over n cubed, and all of this has a sign in front of it, right? This sine of nx in front of it. So why not just have like a common denominator and stuff right here? Why not have a common denominator of n cubed? So you'll have to basically multiply both sides by, multiply the numerator and denominator by n squared on the first fraction, and we can pull out the 2. So we have 2 times sum from n equals 1 to infinity of minus 1 to the n plus 1 n squared pi squared plus 6 times minus 1 to the n divided by n cubed times sine of nx. Well, fair enough, right? This is f of x. But then again, what is f of x? X cubed, right? We defined this to be x cubed. So x cubed can be expressed as this. It's a surprising fact, but it's true. Infinite series, infinite sines superimposed on each other, having this varying coefficient with n, can actually mimic the graph of x cubed. And this replication is highly accurate because we have an infinite sum. So we are doing this process of superimposing infinitely, so that that removes any imperfections we have in the limit as n goes to infinity. Anyways, too much of daydreaming there. So we can have x cubed now written as two separate series. So first series is 2 pi squared times sum from n equals 1 to infinity of minus 1 to the n plus 1 times the sine of nx divided by n plus 12 times sum from n equals 1 to infinity of minus 1 to the n times the sine of nx divided by n cubed. But what is this? This is just our s, right? The sum we needed to find. That's why this Fourier series is brilliant. That the question that we had, the problem that we needed to solve, just came out as a byproduct of this Fourier coefficient calculation and stuff. But fine, we know this is s, but what can we make of this? Well, firstly, before doing anything, let's take x equals 1. Then we'll have a single n like our s, right? Because there was no x in our original problem. There was sine of n, no x. So when we take x equals 1, we get rid of the x. So we have 1 cubed, which is 1, is equal to 2 pi squared, and then sum from n equals 1 to infinity of minus 1 to the n plus 1 times the sine of n divided by n plus 12 times, now this is s. Let's just write it as it is, s. And I want to split the sign in terms of its exponential definition. So we have 1 is equal to 2 pi squared over 2 pi sum from n equals 1 to infinity of minus 1 to the n plus 1 times e to the sine of n is e to the I n minus e to the negative I n divided by 2i. So we took the 2i outside, and we have e to the I n, which can be represented as e to the I but raised to the nth power divided by n, minus the similar expression 2 pi squared over 2i times sum from n equals 1 to infinity of minus 1 to the n plus 1 times e to the minus I to the n divided by n plus 12s. But notice this is similar to a Taylor series that we know. Yes, that's right. The natural log, the Taylor series of the natural log. So we can write this as 2 pi squared over 2i times natural log of 1 plus argument that was basically raised to the nth power in the series. So 1 plus argument is e to the I in this case, minus 2 pi squared over 2i, and then this is going to be natural log of 1 plus e to the negative I in this case plus 12s. Using log property, let's group some terms. We have 2 pi squared over 2i and natural log of 1 plus e to the I divided by, I can write this in terms of positive exponents. So we have e to the I plus 1 divided by e to the I. So notice this and this cancels out and e to the I goes on top. So we have 1 is equal to 2 pi squared over 2i times the natural log of basically e to the I plus 12s. Cancel the 2's out. 1 is equal to pi squared over I, and we can use basically the uh, properties of logarithms to have I times natural log of e plus 12 as natural log of e is 1 by definition, so and the i's cancel out, giving us 1 is equal to pi squared plus 12s. This means s is equal to 1 minus pi squared, the entire thing divided by 12, and that's the the grand answer that we have. So this is a really powerful technique of using Fourier series to calculate stuff. But as you might have guessed, this works when we have a trigonometric terms like the sine and the cosine, because those were terms included in the Fourier series part, right? For other trigonometric terms, it would be slightly challenging, but you get how powerful this technique is, right? You can do all sorts of things. We can have n to the fourth power, n to the fifth power, in which case we would have to take f of x equal to, in the case of n to the fourth, we have to take x to the fourth, and vice versa and stuff like that. But then again, there is a catch, because there is a shortcut technique. And noticing the n cubed in the denominator and this um, infinite series going from n equals 1 to infinity, you might be reminded of some polylogarithm functions. Polylogarithm functions, which were basically, say, if you have a polylog to the base, I don't know, s of some variable x, that was defined as sum from k equals 1 to infinity of x to the kth power divided by x to the s. And in this case, s is 3, right? That variable cubed, right? So it's a special case of the polylogarithm, or polylogarithm of order 3, which is called the trilogarithm. So the trilog of x is equal to sum from k equals 1 to infinity of x to the kth power divided by k cubed. And we have that, so we can somehow convert the sine into its exponential definition, and we could try to do something with trilogarithms. So this becomes sum from n equals 1 to infinity of minus 1 to the n times e to the I to the nth power divided by n cubed, and we have to divide by 2i, right? Because sine of theta is equal to e to the I theta minus e to the negative I theta divided by 2i. That's why we're splitting them into two sums. Minus sum from n equals 1 to infinity of minus 1 to the n times e to the negative I to the nth power divided by 2i n cubed. We can, since we don't have this alternating part, we can just take the alternating part along with the e to the I in a common argument to negative e to the I whole thing to the nth power divided by 2i n cubed minus sum from n equals 1 to infinity of minus e to the negative I whole thing to the nth power divided by 2i n cubed. And now we can just represent this using this definition as 1 over 2i, and in the bracket the trilogarithm of the inside expression negative e to the I minus the trilogarithm of minus e to the minus I. Well, what can we do beyond this? And it turns out there is this beautiful identity with trilogarithm. So if you have trilogarithm of negative z minus the trilogarithm of negative 1 over z is equal to basically minus 1 over 6 times natural log cubed of z minus 1 over 6 times pi squared times natural log of z. And z can even be complex number. So we can write this now as 1 over 2i. We can see that z is just equal to e raised to the I, and 1 over z evidently is e to the negative I. We have everything satisfied. It's almost like this identity was tailor-made for this question. So we have 1 over 2i times, using this right hand side of this, minus 1 over 6 times natural log cubed of z, which is e to the I, minus 1 over 6 times pi squared of natural log of e to the I. And we have, using power rule, we have I cubed, because natural log of e the whole thing cubed is going to be 1. So we have 1 over 2i, and I cubed is negative I, so that gets rid of this negative. We just have an I over 6 minus 1 over 2 pi times I, that will come down, natural log of e is 1, pi squared over 6. So notice that the i's will nicely cancel out, giving us a completely real answer, which is 1 over 12 minus pi squared over 12, which is basically 1 minus pi squared over 12. And in case you want to write this in terms of Riemann zeta functions, this is minus Riemann zeta of negative 1 and minus half of the Riemann zeta of 2. Well, Riemann zeta of negative 1 is basically sum of all integers, basically n equals 1 to infinity of n, which is 1 plus 2 plus 3 plus 4. And there's a real new branch of mathematics, completely different branch of mathematics, that deals with assigning values to these sums, like that comes under regularization, in this case zeta regularization, and analytic continuation of the Riemann zeta function, which constitutes a great part of the Riemann hypothesis, and it's an open problem. So basically, in that branch, this series is assigned minus 1 over 12, although it doesn't have any physical significance, right? Because otherwise, in the conventional sense, this is just diverging to infinity. But in that branch of mathematics, if you consider the analytic continuation along with like zeta regularization and stuff, then we have minus 1 over 12, and that's what I wanted to represent over here. Minus of minus 1 over 12 is 1 over 12, and Riemann zeta of 2 is pi squared over 6. Half of that is pi squared over 12. So, we basically have this nice result by two different methods. I don't know which method you prefer, but in all cases, Fourier rules and polylogarithms are resourceful. I mean, if we didn't have this identity over here, we would be doomed, right? Completely doomed. But it's almost tailor-made for this question. So that's it for this video, guys. So hey guys, please like, share and subscribe to my channel. Recommend me to your friends, fellow mathematicians, number files, people who want to learn everything, people who are jobless during this time and want to start doing mathematics from scratch, whatever. So just like, share and subscribe. You can follow me on Instagram, gamma_digamma. In the meantime, stay home, stay safe, great day, peace out.